surface areas and volumes. Introduction. In your earlier classes, we have learnt about the surface areas and volumes of a number of solids such as cuboid, right circular cylinder, right circular cone, sphere, etc. We are familiar with the shapes of these solids and also know the formulae required to find their surface areas and volumes. In our day-to-day life, we need a number of solids which are either a part of such a solid or a combination of these solids. For example, a bucket containing water is a part of a right circular cone, and a conical circus tent with round base walls is a combination of a right circular cylinder and a right circular cone. In this chapter, we shall deal with problems of conversion of a solid into another, surface area and volume of a part of a solid, including frustrum of cone, surface areas and volumes of combinations of solids. Let us review the formulae related to the surface areas and volumes of those solids which you have already learnt in your earlier classes. Review of surface areas and volumes of solids. In this chapter, we shall remind ourselves the formulae related to surface areas and volumes of solids such as cuboid, cube, right circular cylinder, right circular cone, sphere, etc. Cuboid. L. Length of cuboid. B. Breadth of cuboid. H. Height of cuboid. Total surface area is equal to 2 into LB plus BH plus HL, the whole. Lateral surface area is equal to 2 into BH plus HL is equal to 2 into L plus B, the whole, into H. Volume is equal to L into B into H. Cube L, length of an edge. Total surface area, 6L squared. Lateral surface area, 4L squared. Volume, L cubed. Right circular cylinder, R, radius of the base, H, height, or length. Area of base, pi r squared. Carved surface areas, 2 pi r h. Total surface area, 2 pi r squared plus 2 pi r h is equal to 2 pi r into r plus h the whole. Volume is equal to pi r squared h. Bellows cylinder, R, internal radius, capital R, external radius, h, height. Area of base is equal to pi into capital R squared minus lower r squared. Curved surface area is equal to 2 pi into capital R plus lower r, the whole, into h. Total surface area is equal to 2 pi capital R plus lower r, the whole, into h plus capital R minus lower r, the whole. Volume of material is equal to pi into capital R squared minus lower r squared, the whole, into h. Right circular cone, R, radius of base, h, height, L, slant height. Area of base is equal to pi r squared. Curved surface area is equal to pi rl. Total surface area is equal to pi r squared plus pi rl, which is equal to pi r into r plus l the whole. Volume is equal to 1 by 3 pi r squared h. Sphere, R, radius, surface area 4 pi r squared, volume 4 by 3 pi r squared.
Note, Sum 1. For a hemisphere of radius r, we have curved surface area equal to 2 pi r square. Total surface area equal to 3 pi r square. Volume equal to 2 by 3 pi r square. Sum 2. For a spherical shell with inner radius small r and outer radius capital R, the volume of the mate required is 4 by 3 pi into capital R cube minus small r cube.
The table given on the screen is very useful to learn the formulae for finding surface areas and volumes of right circular cylinder, right circular cone, sphere and hemisphere. Conversion of solids. For public works and for industrial development activities, we need to convert a solid into another solid of different shape or more than one solids of similar shape but with reduced size. Theorem. If capital R and low r are respectively the outer and inner radii of a spherical shell, that is, hollow sphere, then the material in the shell is of volume 4 by 3 pi into r cubed minus v cubed the whole, cubic units. If capital R and lower r are respectively the external and internal radii of a cylindrical shell of height h, then the material in the shell is of volume pi h into capital R squared minus lower r squared cubic units. If x cubic units of a liquid is filled in n cylindrical shaped containers of radius small r and height h, then we have n into pi r squared h the whole is equal to x, or n is equal to x by pi r squared h. If x cubic units of solid material is consumed for making n spherical balls of radius r, then we have n into 4 by 3 pi r cubed the whole is equal to x, or n is equal to 3x by 4 pi r cubed.
The radius of the metallic sphere is 9 cm. The sphere is melted and drawn into a wire of uniform circular cross section. If the length of the wire is 234 meter, find the radius of the cross section. Solution. We are given that the radius of the given metallic sphere is equal to 9 cm and length of the wire is equal to 243 meter, that is 24,300 centimeter. Let the radius of the cross section of the wire be r centimeter. The volume of the wire is equal to the volume of the sphere, that is pi r square h is equal to 4 by 3 pi r cube. Substituting the value of r as 9 centimeter and h as 24,300 centimeter, we get r is equal to 0.2. Hence, the radius of the cross section of the wire is equal to 0.2 centimeter. The diameter of the solid sphere is 16 centimeter. The sphere is melted and recast into 8 equal solid spherical balls. Determine the radius of the balls. Solution. We are given that the diameter of the given metallic sphere is 16 centimeter. Its radius 16 by 2 is equal to 8 centimeter. Let r be the radius of each spherical ball. The volume of the 8 spherical balls is equal to the volume of the sphere. 4 by 3 pi r cube into 8 is equal to 4 by 3 pi into 8 cube. Implies r cube is equal to 8 cube by 8. Implies r cube is equal to 64. R is equal to cube root of 64, which is equal to 4 centimeter. The decorative block shown in the figure made of two solids, a cube and hemisphere. The base of the block is a cube with edge 5 centimeter and the hemisphere fixed on the top has diameter of 4.2 centimeter. Find the total surface area of the block. Solution. The total surface area of the cube is equal to 6 into h square is equal to 6 into 5 into 5 centimeter square, which is equal to 150 centimeter square. The surface area of the block is equal to total surface area of the cube minus base area of the hemisphere plus curved surface area of the hemisphere is equal to 150 minus pi r square plus 2 pi r square is equal to 150 plus pi r square. Substituting the values of pi and r in the formula, we get total surface area of the block is equal to 163.86 centimeter square. A hemispherical bowl of internal diameter 36 centimeter is full of liquid. The liquid is to be filled into cylindrical shaped bottles, each of radius 3 centimeter and height 9 centimeter. How many bottles are required to empty the bowl? Solution. Internal diameter of the hemisphere bowl is equal to 36 centimeter. Therefore, the radius of the bowl is equal to 18 centimeter. The volume of the liquid in the bowl V1 is equal to 2 by 3 pi into 18 cube centimeter cube. The volume of liquid filled in the bowl is V1 is equal to 2 by 3 pi into 18 cube centimeter cube. The radius and the height of the cylindrical bottle are 3 centimeter and 9 centimeter. The volume of the liquid filled in the one bottle is V2 is equal to pi into 3 square into 9 centimeter cube. Let the number of bottle required be n. The volume of the liquid in a bottle n into V2, n into V1 into V2 is equal to n is equal to V1 by V2. Substituting the values of V1 and V2 in the formula, we get n equal to 48. A well whose diameter is 7 meter has been dug 22.5 meter deep. The earth dug out is used to form an embankment 10.5 meter side around it. Find the height of the embankment. Solution. Radius of the well is equal to 7 by 2 meter. Depth of the well is equal to 22.5 meter, which is equal to 45 by 2 meter. The volume of the earth dug out is V1 is equal to pi into 7 by 2 the whole square into 45 by 2 meter cube is equal to pi into 7 by 2 into 7 by 2 into 45 by 2 meter cube. Now, the inner radius r of the embankment is equal to 3.5 meter and outer radius r of the embankment is equal to 3.5 plus 10.5 is equal to 14 meter. Let the height of the embankment be h meter. The volume of the earth used for embankment is area of the base of embankment into height is equal to pi into capital R square minus small r square into h is equal to pi into capital R plus small r into capital R minus small r into h is equal to pi into 14 plus 3.5 into 14 minus 3.5 into h is equal to pi into 17.5 into 10.5 into h meter cube. Since volume of the earth used is equal to volume of the earth dug out, therefore V2 is equal to V1. Substituting the values of V1 and V2 in the formula, we get h is equal to 3 by 2 is equal to 1.5 meter. Therefore, height of the embankment is equal to 1.5 meter. Water is flowing at the rate of 5 km per hour through a pipe of diameter 14 centimeter into a rectangular tank which is 25 meter long and 22 meter wide. Determine the time in which the level of water in the tank will rise by 21 centimeter. Solution. We are given that the radius of the pipe is equal to 7 centimeter is equal to 7 by 100 meter. Volume of the water flowing through the cylindrical pipe in 1 hour at the rate of 5 km per hour is equal to pi into 7 by 100 the whole square into 5000 meter cube. That is, 1 kilometer is equal to 1000 meter. We get 77 meter cube. Level of water to be raised in 25 meter into 22 meter water tank is equal to 21 centimeter, which is 21 by 100 meter. The volume of the water added into the water tank is equal to 25 into 22 into 21 by 100 meter cube, which is equal to 231 by 2 meter cube. Let the required time to raise the water level in the tank by 21 centimeter be T hours. Therefore, 77 into T is equal to 231 by 2 implies T is equal to 231 by 2 into 1 by 77 implies T is equal to 3 by 2 hour.
Surface areas and volumes of combinations of solids. In this section, we shall explain the method of finding surface areas and volumes of solids which are by the combination of basic such as right circular cylinder, right circular cone, sphere, hemisphere, etc. For example, a circus tent consisting a cylindrical base surmounted by a conical or hemispherical top, a toy in the form of a cone mounted on the base of a hemisphere, etc. We shall illustrate the method of determining surface areas and volumes of such combinations of solids through examples below. Volume of solid in figure is equal to 2 by 3 pi r cubed plus 1 by 3 pi r squared h. Surface area is equal to 2 pi r squared plus pi r root of h squared plus lower r squared the whole is equal to 2 pi r squared the whole plus pi rl. Volume of solid in figure is equal to pi r squared h1 the whole plus 1 by 3 pi r squared h2. Curved surface area is equal to 2 pi r h1 plus pi r root of h2 squared plus r squared is equal to 2 pi r h1 the whole plus pi rl. Area of base is equal to pi r squared. Frustum of a right circular cone. In our day-to-day life, we come across a number of solids of the shape as shown in the figure. For example, a bucket or a glass tumbler. We observe that this type of solid is a part of a right circular cone and is obtained when the cone is cut by a plane parallel to the base of the cone. If a right circular cone is cut off by a plane parallel to its base, the portion of the cone between the plane and the base of the cone is called a frustum of the cone. We can see this process from the figures given below. The lower portion in figure is the frustum of the cone. It has two parallel flat circular bases, marked as base 1 and base 2. A curved surface joins the two bases. The line segment MN joining the centers of the two bases is called the height of the frustum. Diameter CD of base 2 is parallel to diameter AB of base 1. Each of the line segments AC and BD is called the slant height of the frustum. We observe from the figures that height of the frustum is equal to height of the cone OAB minus height of the cone OCD. Slant height of the frustum, the slant height of the cone OAB minus the slant height of the cone OCD. Volume of a frustum of a right circular cone. Let h be the height, r1 and r2 be the radii of the two bases, r1 greater than r2 of frustum of a right circular cone. The frustum is made the complete cone OAB by cutting of the conical part OCD. Let H1 be the height of the cone OAB and H2 be the height of the cone OCD. Here H2 is equal to H1 minus H. Since right-angled triangles OND and OMB are similar, therefore we have H2 by H1 is equal to R2 by R1. From the above, we get volume V of the frustum of the cone is equal to volume of the cone OAB minus volume of the cone OC. Curved surface area of a frustum of a right circular cone. Let H be height, L be slant height, and R1, R2 be the radii of the bases where R1 is greater than R2. In figure, we observe EB is equal to R1 minus R2 and T squared is equal to H squared plus R1 minus R2 the whole squared. L is equal to root of H squared plus R1 minus R2 the whole squared. In figure, we have OAB as the complete cone, from which cone OCD is cut off to make the frustum ABDC. Let L1 be the slant height of the cone OAB and L2 be the slant height of the cone OCD. Since triangle OND and triangle OMB are similar, L2 by L1 is equal to R2 by R1, which gives L1 minus L by L1 is equal to R2 by R1, which gives L1 is equal to LR1 by R1 minus R2. Now, L2 is equal to L1 minus 1 is equal to LR1 by R1 minus R2 by L, which again gives L2 is equal to LR2 by R1 minus R2. Curved surface area of frustum ABDC, which is equal to curved surface area of cone OAB minus curved surface area of cone OCD, equal to pi L R1 squared minus R2 squared by R1 minus R2 the whole. Therefore, curved surface area of frustum is equal to pi L is equal to R1 plus R2 the whole. Total surface area of a frustum of a solid right circular cone. Let H be the height, L be the slant height, and R1, R2 the radii of the bases, where R1 is greater than R2 as shown in figure. Total surface area of this frustum is equal to curved surface area plus area of base 1 plus area of base 2 is equal to pi 1 R1 plus R2 the whole plus pi R1 squared plus pi R2 squared. Area of the metal sheet used to make a bucket. A bucket is in the shape of a frustum of a right circular hollow cone. Let H be the depth, L be the slant height, R1 be the radius of the top, and R2 be the radius of the bottom as shown in figure. The area of the metal sheet used for making the bucket is equal to outer or inner curved surface area plus area of bottom is equal to pi L R1 plus R2 the whole plus pi R2 squared. The capacity of the bucket in figure is equal to its volume, that is equal to 1 by 3 pi H into R1 squared plus R1 R2 plus R2 squared the whole. For a frustum of a right circular cone, H is equal to height or depth, L is equal to slant height. Capital R or R1 is equal to radius of base 1, R or R2 is equal to radius of base 2. A1 is equal to area of base 1, A2 is equal to area of base 2, V is equal to volume. CS is equal to area of the curved surface. TS is equal to area of the total surface. Some important results are shown on the screen.
A bucket of height 16 cm and made up of metal sheet is in the form of frustum of a right circular cone with radii of its lower and upper ends as 3 cm and 15 cm respectively. Calculate first the height of the cone of which the bucket is a part. Second, the volume of the water which can be filled in the bucket. Third, the slant height of the bucket. Fourth, the area of the metal sheet required to make the bucket. Solution. Let ABCD be the bucket which is frustum of a cone with vertex O as shown in the figure. Let ON is equal to x centimeter. Triangle ONB is similar to triangle OMC.